What I would like to do is introduce our three speakers for tonight. So we have to the left, John Norbury is our fellow speaker for tonight. He is an emeritus lecturer at the Oakshott Center for Industrial and Applied Mathematics. He's originally from Australia, and he studied applied mathematics in Cambridge, where he graduated with DPhil. And after working for a while at UCL, he came to Oxford, where his research has been focusing on applying mathematical models to different real-world systems, for example, in biological systems, in fluid dynamics, and, which is most relevant for tonight, also in weather forecasting. John Norbury also co-authored a very interesting book on the history of how weather forecasting was influenced by mathematical models in the 20th century. The book is entitled Invisible in the Storm, and I invite you, if you are interested and want to know more about the topic, to go and have a look. Then next up we have our alumnus speaker, Professor Paul Williams. He's a professor of atmospheric physics at the University of Reading, and he studied physics at Lincoln College. And his area of expertise is atmospheric physics, turbulences and climate change, and he's particularly noted, among other things, for his studies on how climate change could actually increase the amount of air turbulence. For example, this would have an effect on turbulence during flights. Then we have our student speaker, Sofija, who is doing a master's in mathematical and theoretical physics here at Oxford. She graduated last year from Amsterdam, where she studied with a major in physics. And her area of interest is theoretical condensed matter physics, and especially she's interested in researching new and interesting states of matter that could potentially have applications in new technologies such as quantum computing. But we'll also see from her talk that her interests actually go far beyond physics, but I will not want to spoil anything, and I'll leave the rest to her. So without further ado, I would like to open the actual discussion, and so I would like to invite John Norbury to take the stage.
Well, hi. So this is, I'm going to find out how this works. That's it. So today being sort of 2019 and Valentine's Day, for me it's got a very, very small point that the book that I'll advertise a little bit later, the book is apparently appearing with Springer Verlag in German today. So for those of you who actually speak and write and read German, you could even look at it in German. Unfortunately, I don't, so I don't know what sort of a job they've done. Anyway, the point of this transparency is just to say this is where all numerical forecasting began. So what's the importance of numerical weather forecasting if, in fact, what you really want to do is look at the impacts of our actions on climate? And so you might say, well, this has got nothing to do with it. Well, yes, actually, because even if this set of machinery can't actually predict the weather very accurately, you could at least explore changes. So if you make changes to what you're doing with the actual atmosphere, you could look at the effect of changes using computer simulation. So that's what lies behind big computers these days and big weather forecasting programs. So the fun of this diagram, I mean, I could spend the whole time talking about the people in the pictures and what that says about society, but that was 1950, first successful computer forecast of a real-world problem. What was occupying that room at MIT was their first computer, and even it had to be, the data had to be manually entered. So the data was entered and put in on cards, and it took 24 hours. Now for fun, it was all reproduced on a Nokia handphone 20 years ago, just to check whether or not the original calculations had all been accurate, but also just to see how much a little Nokia handphone 20 years ago would do. That forecast on that machine on the previous transparency took a month to actually run. and the Nokia took 1 minute, including data entry and pictures coming out. Okay, so there's the book that first came out, and it's just coming out in German. So that's global weather. That's what we're trying to predict and look at. And as it goes on, what we want to know is, what are we doing that's changing the weather? And are there other things that we could do that might change it in other ways? Okay, so that's weather. And looked at from our point of view, that's weather. And when you look at that, you realise it's just not possible to compute all of that. Neither in this decade nor in the next. So pretty well by the time everybody in this room has pretty well finished their scientific and professional careers, even then you will discover that you still aren't predicting everything in this picture. Okay? You might be trying to predict the main features of that picture, but I don't think you'll be predicting that. Okay, so I'm not going to sort of talk about any of that. The climate people, of course, are worried about inputs and outputs. So solar input is the main thing, and really what we do to the solar input and how it goes out is what we're worried about. And I'm not going to talk about it too much. So this is what I will talk about a little bit. So why is it so hard? And why did they choose weather forecasting as the first problem to run on a practical public computer? Of course, in the Second World War, they had been running computers to do secret things, but this was the first public computation that was being run 70 years ago. And so why 70 years, why haven't we actually cracked this problem? So it was chosen because at the time people thought it was going to be one of the hardest mathematical problems to solve on a computer, point one, and point two, that it would be of widespread interest. And that's probably still relevant. So we're still not even solving it now. So nearly 20 years ago, the chief astronomer made a speech for the millennium 1900, and he said, I can predict two things. One is that in 100 years' time, my predictions about the comets will come true, and in 100 years' time, they still won't be able to forecast the weather even for the week ahead. And he was pretty right. Okay, so why? Well, if you look at these numbers, those are the pressures in millibars at sea level or ground level. And you see they don't vary very much in the horizontal over thousands of kilometres. What you might not be able to see very clearly, if I can get a red dot to come out. So there's the UK, so there's the North Atlantic, and there's bits of Canada. So that's the scale. This is Western Europe. Here's the Mediterranean down here. So that's a big scale on the globe, and yet we're only moving by perhaps 60 or 70 millibars. If you actually look at pressures here over a week or two, the pressures will go up and down by no more than perhaps 20 or 30 or maybe 50 millibars. And yet, if you go up 5 kilometres, the pressure will go down by 700 millibars. So there's an absolutely, and that's 5 kilometres, 700 millibars that way, and compared with time and space horizontally, very few millibars. So it's that mismatch between the vertical and the horizontal that's the whole problem with weather forecasting, and with actually trying to understand and do something about it. Okay, so, and why is the vertical then such a problem, or why in fact can we forecast anything at all? It's because most of the time, most of the weather is fairly layered. So you go out, for instance, in the nice areas of the world, not necessarily here, but in other areas of the world, and you'll see nice sunny days, and you'll see calm layers of cloud, and maybe even no cloud at all, and everything will be quite horizontally layered, and quite gentle and peaceful, for most of the time. Okay, so that's the horizontal layering of the pressure in the atmosphere. Very small perturbations to it then cause quite dramatic movements of weather in the horizontal. And those little perturbations come from small changes going up and down in the vertical. And those changes are caused by heat and moisture. So what people can forecast is sort of pressure and to some extent temperature and winds, but precipitation they have a real problem with. So clearly if you pick an area where the precipitation's not changing very much, like the Antarctic in winter, for instance, or the Sahara for most of the time, or the centre of Australia in the summer, and etc., etc. You can make a forecast for a few months ahead about the amount of rain that will fall. But otherwise, in places like the western edges of continents, such as Vancouver or the UK, the rain is sort of maybe yes, maybe no. So from that point of view, your forecast will look very bad. So it depends on what criterion people judge you. If they judge you on whether or not you've got plus or minus 2 millibars of pressure, you'll do a good job. And if they measure you, and if your salary determines on whether or not you actually got rain or didn't get rain, then you're in more trouble. I would look for a different job. Okay, so there are equations about this, and I'm not going to go into the equations. I'm not going to go into any of that. So the jet stream, you might argue, is a big signal of what's going on and a big control of what's going on. So you might argue that if you really want to influence the weather, what you've got to do is influence the actual jet stream. And if you think about it that way, then it becomes a lot harder. You've actually got to do a lot. So for instance, 20 years ago, geoengineering for the new millennia, people talked about, would you be able to put enough aluminium foil up in the stratosphere to reflect off the sun's radiation? So large numbers of satellites with giant umbrellas, parasols. So people pretty quickly realised that was crazy. And then there were things like, I'm hopefully not going into what you're going to talk about, but another idea that I didn't particularly like the sound of was that every jumbo jet flying across just underneath the stratosphere would leave behind lots of muck. And that this muck would actually affect the solar radiation going in and out. So those are the sort of things on the big scale that you might think of doing. So I'm not going to talk about any of that, nor am I really going to talk about the equations, except to say that how do you in practice forecast? You actually finally realise that you avoid doing the conventional things in the vertical because you just can't do them. So you drop Newton's equations in the vertical. Okay, so this is, if that red pointer comes out, yeah, there it is. So there is Newton in the horizontal, Newton's acceleration and forces in the horizontal. And there's the pressure gradients driving the accelerations in the horizontal. But the trouble is this pressure gradient in the horizontal is being affected by what you're doing in the vertical. So what I've left out of all of this is the water vapour. And the water vapour, thanks. The water vapour is, of course, what it's all about. Really, I think, in terms of climate change, if we were all told that climate change is plus or minus 2 degrees, none of us would really be worried too much. That would apply for, I think, at least 90% of the world's population. What affects most people around the world who are really concerned about this is the water levels, precipitation, etc. So you're worried about it for several reasons, such as crops, harvesting, growing things, forests, animal species that live in these forests, live on these grasslands. You're worried about all those things. Latest thing is insects. You've seen them in the papers in the last week. And the other thing, of course, is sea levels. So it would be a bit dramatic if, in fact, all the ice actually melts and the sea levels start to change dramatically. So if you take a look at the Earth's atmosphere through different sort of cameras, what you see is this water vapour. And that's what we're really trying to predict and sort of maybe alter if we're able to. Okay, so I'm down to what, almost 1 minute, so I'll just, and I don't, so I did actually have some equations, I actually said I didn't. So that's what I wanted to get to. So that's what the atmosphere and weather really look like. It's a thin horizontal, of large extent horizontally, but quite thin vertically. So there's on a piece of the planet, and there are all these clouds which are vertically taking up heat and moisture. And the computers, or our ability to actually model and predict all of this sort of thing accurately is very small. So therefore you might think, well, this is pretty hopeless. If we can't actually predict weather, for instance, 1 week ahead, then how on earth can we say anything about climate? So as I started, I'll sort of wind up by saying, we think that maybe by using the computer as a simulator of potential or possible weather and running it hundreds of times, we can then look at things that we might do. So you might say, oh well, what the heck, we're in a sort of slightly tricky situation. We'll just throw mega engineering at the problem on this planet and just see what happens. If you're a bit more cautious, you might say, is there some way that we could test? Could we run an experiment? Well, when you think about running an experiment, you think that's pretty hard. So maybe what you have to do in the end is run a numerical experiment and look at changes and see what the effect of the changes is. And see whether or not any of them go wrong. Because we're not very good at making changes in nonlinear situations, and then we get what are called unintended consequences. Okay, so I'm just being shown the 1 minute board, so I ought to wrap up. So I think this is probably about the right time to hand over for climate. So whether we're doing a better and better job, we're now facing up to the issues of how to model these movements in the vertical of heat and moisture. So apart from being nonlinear and various other sort of technical issues, because when you condense water vapour, you release a lot of energy. So that was the other thing I meant to say. The sort of energy released from 1 degree of heat raising of a parcel of air is equivalent to around about 40 kilometres an hour of horizontal or air movement. So if you've ever stuck your hand out of a car window as you've been going down the motorway and you feel the air pressure on your hand, or if you've been out in a gale, you can get that from 1 degree temperature rise. So the heat and the moisture in particular, as the moisture rises and condenses, it releases very large amounts of heat. And that's what powers hurricanes, tornadoes, and that in fact is what leads to changes in the climate. Okay, so I should hand on. Thank you.
Well, good evening everyone. It's a really great pleasure to be here back in Lincoln, exactly 20 years after I graduated in 1999. And in fact, the prospect of coming back to Lincoln prompted me to blow the dust off some old photograph albums of my Lincoln days. So I'm going to potentially embarrass myself in the next slide by showing you a photo from 1996, I think. Back in my old room, Lincoln House 24, I remember it very well. Yes, haven't changed a bit, have I? If only. But that's there actually to remind me that I wanted to share an anecdote with you about my time here at Lincoln. And it's very pertinent to the subject tonight because it's about chaos theory. I studied physics here, a 4-year undergraduate physics degree, and in my 4th year I had to choose which options to specialise in. And I'd chosen chaos theory as one of my options. And in those days, the way you communicated your choice to the university was that you had to go to the college office, to the college secretary, and tell the secretary, and she or he communicated that to the university. I'm sure there's a much fancier way of doing it today, an online portal where the students can lie in bed in their pyjamas and choose their options. But in those days, you had to physically go to the college office. And I'm sure many of you here have been in the Lincoln College office, a hive of activity, at least it was in my day. Fellows, students coming and going, a printer constantly at work, computers beeping, the telephone didn't stop ringing. I'm certain there was a fax machine back in those days as well. So really just a hive of activity, constantly things going on. And I knocked on the door and went in and said, I'd like to study chaos, please. And the college secretary just paused for a few seconds and just surveyed her working environment, and then she looked back at me and she said, I could teach that course in my sleep. But I studied chaos, and in fact that's really the path that led me onto my current career as an atmospheric scientist. So that's how it all began. So thank you, Lincoln, for a wonderful 4 years here. It was a really special time, and I always remember it, and I always will. When I first saw the subject for tonight, so one of my possible interpretations was that it was about deliberate weather modification. So not climate change by putting carbon dioxide into the atmosphere, but trying to change the weather tomorrow by doing something like making clouds appear in the atmosphere. And indeed that is possible. So the theory behind this is that if you have some water vapour molecules in the atmosphere, they find it very hard to condense into raindrops unless there's something in the atmosphere, dust or salt or ash particles, for them to condense onto. Very clean air, it's very hard for raindrops to form in clouds. We need dirt in the atmosphere. So the idea is that by deliberately, as John very eloquently suggested in his talk, by deliberately putting soot or dust into the atmosphere, we can cause those water vapour molecules to start to condense, form raindrops, form clouds, and rain. And if you force all of the water out of the atmosphere here, then what that means is that a few kilometres down the road, it's not going to rain. And if, for example, it's your wedding day on the 20th of June 2019 or whatever, there are companies you can pay if you have £100,000 in your back pocket, and they claim to fly an aeroplane out, put some dirt into the atmosphere, and force all of the water vapour out of the atmosphere, so that the place where you're going to get married, it's going to be blue skies and sunny weather. Just as an aside, if you want to make some money one day, I have a business plan, which is to set up a company like this, but don't do anything. You just sit back and you take the £100,000 and you just relax. And if it happens to be sunny anyway, then you claim victory and you keep the money. If by chance it rains, well, there's a money back guarantees and you give the money back. But on average, you're like £50,000 up per transaction. So you get very rich very quickly. If you're an unscrupulous person, which I'm sure we're not. But on reflection, I thought what I'd focus my talk on is a direct rebuttal of some of the, frankly, idiotic comments that come from climate change skeptics. And this is a typical comment, and it's all about how can we say what the climate will be in decades into the future when we can't even forecast the weather in the next few days. And that's a very seductive, logical argument, isn't it? Because we all know that the further out in time you go, the worse the weather forecast is. That's certainly true. And therefore, logically, if you don't really know what you're talking about, logically, you can make it seem plausible that, therefore, our possibility of predicting the climate in the middle of this century is virtually zero. Well, in fact, that's idiotic nonsense, and I'm going to deconstruct and take this apart in my remaining time. I mean, this tweet is wrong in so many different ways. I mean, I could give a whole lecture about this, but I mean, so we can say a lot actually about what's going to happen in 6 months' time. In 6 months' time, it'll be summer, it'll be August, it'll be nice and hot, almost certainly hotter than it is today. So there is predictive skill just because of the seasons. And this, I'm having a bit of a rant here, aren't I? The second thing that's wrong is the Met Office routinely gets its weather forecast wrong tomorrow. This is just idiocy. There may be 1 or 2 days a year when there's something slightly wrong about the forecast, and here's the evidence for that. From a study published in Nature, this shows how the accuracy of weather forecasts has improved since the 1980s. So the blue curves are for the weather forecast 3 days ahead, red is 5 days ahead, yellow is 7, and the grey is 10 days ahead. So it's forecast scale going all the way up to 98.5%. There's a range because the northern hemisphere and the southern hemisphere are different. Historically, we've been better at forecasting weather in the northern hemisphere because it's been better observed. But as you see, that gap between the northern and the southern hemispheres has reduced over time because of satellite observations, essentially, so that now there's not really a difference between the two hemispheres. So what's impressive about this is that in all 4 cases, the forecast skill has gone up over time, and that's just because of all of the research that we've been doing to make weather forecasts better. So, for example, today, a 5-day forecast today is about as skillful as a 3-day forecast when I was here at Lincoln 20 years ago. So in that 20-year period, we're now as good at saying what the weather will be 5 days ahead as we were 20 years ago at saying what the weather will be 3 days ahead. And that's a remarkable, it's been called a quiet revolution. There's no step change here, there's no magic bullet that gives us 100% accuracy all of the time, but it's a very gradual but very steady and sure incremental improvement in forecast skill. So, such that now the weather forecast 3 days ahead is about 98.5% accurate, almost never wrong. But the fundamental limit to forecasting the weather is chaos theory and turbulence. And I'm sure you've seen many of these quotes before. Turbulence is the most important unsolved problem in classical physics. Heisenberg imagines meeting God and saying, what were you thinking about? Well, relativity, and also turbulence, and expecting an answer about relativity, but not really for turbulence. And there's variants on this from Horace Lamb, who talks about quantum electrodynamics being a bit mystifying, but he's quite optimistic about getting insights on quantum electrodynamics, but not really about turbulence. And finally, one of my favourite little poems about how turbulent eddies, turbulent vortices on large scales break down into smaller and smaller and smaller eddies and eventually get so small, just a few millimetres big, that friction gets rid of them. Big whirls have little whirls which feed on their velocity, and little whirls have lesser whirls, and so on to viscosity. So why is that tweet wrong? Why is it actually quite easy to predict, not completely trivial, but easy, not too difficult to predict the climate decades ahead when we can't predict the weather 2 weeks ahead? Well, it's because they're entirely different problems. Here's a nice quote from a paper which says that forecasters of the Earth's atmosphere and oceans are confronted by two types of questions. What will happen over the next few hours, days or months as a result of the current configuration of the system? In other words, the state of the atmosphere today. And then on the other hand, what will happen to the climate in the longer term as a result of changed conditions, such as increased CO2? The former, which is weather, depends strongly on the initial conditions, while the latter, which is the climate, is primarily a boundary value problem. So Lorentz, one of my favourite scientists, who basically invented or discovered at least chaos theory, classified these predictions as predictions of the first and the second kind, and they're very different mathematical problems, and that's why we can say something about the climate decades ahead, even though we can't say anything about the weather in a few weeks' time. And let me just illustrate that in my final few minutes by showing you some equations that Lorentz is famous for writing down, a very simple system in which we imagine there are three variables that we're interested in tracking over time, x, y, and z, and here are the equations for them. So if you imagine a point moving around in three-dimensional space according to these equations, so you might start out with a point in space and watch how the system evolves in time. In fact, there are two different simulations running here, a yellow one and a green one, and they're very slightly apart. They have very slightly different initial conditions, a little bit like you might get from a butterfly flapping its wings and creating a little pressure perturbation and changing the initial condition of the atmosphere. And as you can see, they end up doing quite different things. Now, believe it or not, an atmospheric model is not very much more complicated than this problem. The only difference is that you'd have a lot more variables that you wanted to track over time in an atmospheric model. I mean, you'd want the temperature in Oxford, but also the pressure and the humidity and the wind and the air density, but also you'd want to be tracking those variables in Reading as well, and all the way around the world, and all the way up in the atmosphere, and all the way down into the ocean. So you'd have many variables, I mean hundreds of millions of variables in an atmospheric model and an ocean model, but that's really the only conceptual difference between this simple system and an atmospheric model. It's just that we'd have more equations. And my basic point here is that a weather forecast, okay, takes a starting point in this hyperspace and just moves it forward in time. And that is subject to chaotic uncertainty and the divergence of trajectories. That's chaos theory. Slight flaps of a butterfly's wings will inevitably, or at least have the potential to cause the trajectories to diverge, and that's why it's very hard to predict the weather 2 weeks into the future. And in fact, there's a fundamental limit there that we'll never be able to exceed. On the other hand, predicting the climate is a very different problem. The climate is just the bulk properties of this is so-called, this strange attractor, if you like. So if I'm talking about what the climate of this system is, I don't need to worry about individual trajectories, which are subject to chaotic uncertainty. All I care about is the bulk properties, the averages, and the standard deviations of this pattern. And they are not subject to chaotic uncertainty, at least not in the same way. So we can say things about the climate, even though we might not be able to say very much about the weather. They're two very different problems, as Lorenz showed us in that paper. Yes, I'll probably just go into this very briefly. So, for example, these coefficients here determine the climate of this system. Okay, so what we're interested in climate change is how do the properties, the bulk properties of this strange attractor depend on the coefficients of the equations, and we can calculate that without being subject to all of the uncertainties that come from chaos theory. Changing the parameters gives us a different attractor, and we can make confident statements about the averages and the standard deviations of this climate of this system, even though we can't make very skillful predictions of the weather. They're two very different problems. And in my final minute, I think I'll just show you the sort of equations which you've already seen in John's talk that go into a climate model, written in partial differential equation form. John showed you ENIAC, the first computer that was used to make a weather forecast. This is a modern equivalent. This is the Earth simulator in Japan, one of the world's fastest supercomputers. Can do 35 billion calculations a second. Doesn't look like a computer, does it? It looks like a filing cabinet. Actually, if you go downstairs to the floor below, these are the cables connecting together all of the different parts of the computer. It's really an amazing thing to see. And the reality is that when we do climate predictions today, using models like that, on computers like that, it's only by including, if we're trying to simulate the climate change that we know has happened over the past century, it's only by including the carbon dioxide change that we know has occurred because of humankind's emissions of carbon dioxide, that we can replicate the climate change that we know has happened. You can't see the detail here, but the observations, the climate change that we know has happened is in black. It's the same on both curves. The grey band of curves is the model results if we exclude the CO2. So we lie to the computer model. We tell it the CO2 is constant, which we know it wasn't, and it doesn't warm. There's a divergence between the simulation and reality, which is closed up only if we turn up the carbon dioxide in the model in the way that we know it went up in the real system. So that's why, to rebut that classic tweet, and if ever you're in an argument with someone who says, how can we, a climate skeptic who says, I don't believe any of these climate predictions, because we can't say anything about the weather next week. Well, it's because they're very different scientific problems, and the person's making a bit of an idiot of themselves, to be frank, because they don't really understand the mathematics that allow us to make forecasts of the climate and the weather, and the fact that they're very different problems. That's where I'll finish. Thank you.
Thank you, Paul and John, for the expert insight that we've gotten so far. I guess my role in this discussion is probably best described as that of a concerned citizen. I was going to initially talk about quantum computers and how they could potentially be relevant to improving prediction accuracy, because quantum computers are something that is a topic I'm interested in and I would eventually like to be doing research on. But then I realized that the history of weather modification and climate modification is so bizarre that I couldn't really help it but focus on the social and political aspects of it. So rather than addressing whether or not we're able to predict the weather or climate change, I would like for all of us to imagine whether or not we would want to be modifying the weather, even if we could. So even if we had the scenario in which we could modify the path of a hurricane, or we could control precipitation, for instance, with a high level of accuracy, whether or not this is something that would be desirable. There you go. That's the inevitable technical difficulty. Have I mentioned that I'm studying theoretical physics? So before I move on to the weather race, I'd just sort of like to flesh out the aim of my talk tonight. So what I would like to do is look at how weather modification attempts relate to constructive narratives surrounding climate change, and also motivate some of the questions I think need to be asked before we can seriously start thinking about weather or climate modification. The most recent extensive efforts to control the weather find their roots in what has come to be called the weather race between the United States and the USSR during the Cold War, as with many other instances of historical controversy. And on the left-hand side, we see the cover page of Collier's with an article titled "Weather Made to Order" by a US Navy General, Howard T. Orville. And I would actually like to share with you a part of the article, which is one of the many public calls for the use of weather as warfare during the times of the Cold War. So a part of it reads, "We might deluge an enemy with rain to hamper a military movement or strike at his food supplies. But before we can achieve all the benefits I have outlined, hundreds of meteorological unknowns must be solved at a cost of possibly billions of dollars." And what we see in the image accompanying the article is a man controlling the levers of weather control. On the other side of the wall, Stalin introduced a perhaps very typical Soviet great plan for the transformation of nature, which both aimed at boosting the economy of the USSR, but also coexisted with similar aspirations for militarizing the weather that the US had. And while I would like to say that these were just evil fantasies at the time, weather modification did very much become a reality during the Vietnam War. So over the range of approximately 5 years or so, the US was involved in the covert cloud seeding operation where around 9,000 gallons of silver iodide were shot into the clouds above Laos, Cambodia, and Vietnam with the intention of inducing precipitation. So as we've heard from Paul's and John's talks, both of their talks I believe, you need to put in the initial trigger in order to induce precipitation, and this was the more or less untested idea that the US military had at the time and covertly performed during the Vietnam War. So what they realized was that their biggest strategic issue was the fact that they were fighting against the army they were basically not prepared to fight against. And what they ended up trying to do is flood the Ho Chi Minh Trail, induce landscape in Vietnam in order to detract the enemy and in order to sort of win the war by causing environmental havoc. So this was very much reality during the Vietnam War, and it only became known after the act in the so-called Watergate of weather warfare, when this came up at the front page of the New York Times. So as a result of this, we did get a framework which is supposed to prevent people from misusing research into weather modification, and it's called NROD. It's a UN convention which aims to prevent such further misuse of weather modification schemes. And although we don't hear the Cold War era kind of comments which call for weather usage in warfare, there are some important parallels which need to be drawn between these instances and the kind of proposals we see which relate to tackling climate change. So on one hand, you have calls for mitigation of carbon emissions, which are widely supported by the scientific community, but on the other hand, and let's say on the margins, you also have proposals for more interventionist approaches to climate change. So we've already heard some of them, and I'd like to share my personal short list of favorites with you. Some of them are old school and others are more contemporary, but the first one proposes that we could increase global temperature by 1.7 degrees Celsius by injecting a cloud of ice crystals into the polar atmosphere by detonating 10 hydrogen bombs in the Arctic sea ice. And I'm pretty sure the pen over there is actually a result of an extensive calculation, so it's not arbitrary at all. The second one says that we could cover an island with a thin layer of carbon black to absorb heat, while at the same time generating a white smoke screen to make it more reflective, to upset the balance of forces in a passing storm. The first question that came up in my mind whilst reading this was like, have you ever considered whether or not someone lives in these islands, for instance? Which island would we do it on? But I guess that's just a detail. And the third one, which is more contemporary, is to use guns, rockets, or balloons to maintain a dust cloud in the stratosphere to increase the reflection of sunlight. And as John has already mentioned, I believe in his talk, most of these ideas have been discarded and people have realized pretty quickly that they're actually quite stupid. But nevertheless, such proposals still keep coming up. And for researchers involved in the field, they claim to be receiving hundreds of emails with such bizarre proposals, even nowadays. Sorry. Which brings me to one of the first questions I would like all of us to think about and perhaps address in the Q&A, which is, would climate engineering decrease the incentive to reduce carbon emissions? And when talking about the proposals that we've seen, I think it's most appropriate to think about them in the context of them being technological fixes, to borrow a term from James Fleming, who wrote about the history of weather and climate modification. And in this context, technological fixes are solutions which are oversimplified solutions to complex problems, which more often than not lead to generating more problems than they actually fix. And to wonder whether or not it's contradictory for people who support such interventionist approaches to simultaneously believe that we're not capable enough of agreeing to reduce our emissions, whilst also believing that we would be responsible enough to use any potential new technologies in which would be fair, and which would be sort of globally accessible to everyone and used for the common good. So that does seem contradictory to me, but I would also be interested in seeing whether or not anyone would have a different idea. Now, when we're talking about climate change and how we would want to tackle it, the one issue we cannot ignore is the fact that climate change is not equally distributed. So we cannot ignore the fact that there is an imbalance between the biggest global polluters and those countries which end up suffering most acutely from the consequences of climate change. Now, I've decided to use this slide because, which shows the interrelation between income inequality and how much different lifestyles contribute to climate change. Even though it's not country specific, it shows us that around 50% of the pollution in the world is actually generated by the richest 10%. And even though, and given that most of the richest 10% are within the northern hemisphere, it also means that the ways in which climate change affects those who pollute the most and those who end up suffering from it most are not equally distributed. So given that we know this, we might wonder, or might find it easy to imagine that developing new technologies, which aim to modify the weather locally, might turn into yet another resource that fuels the existing climate injustice and inequality we're seeing. Another question I would like for us to explore is how would non-local side effects be accounted for? So we've heard that predicting the climate as a large-scale phenomenon versus predicting the weather as a local phenomenon are two separate issues, but are also interrelated. And then this begs the question of what we would do if there were no local side effects. Who would be responsible for the side effects which would perpetuate? Would there be a way to even account for the responsibility? And ultimately, who would be controlling weather and climate modification schemes? While both engineers and scientists definitely need to be an integral part of the process of tackling climate change and finding effective solutions for it, I think as concerned citizens we should be wary of the kind of technocratic proposals which emphasize the engineering while ignoring the social aspects of an issue that's inherently both global and political. Thank you.
So thank you again to Sofija and the two previous speakers for the very interesting points that were brought up. So first I would like to ask the speakers if you would like to ask any questions to each other, like things that you've seen now during someone else's talk that you would like to know more about.
Well, just to start, you can probably hear me anyway without this thing. So just to start, I'd just like to support Sofia's point that it seems to me the rather crucial first step is who controls the decision-making ability in brackets and is going to make the money out of future attempts to change the climate. So I agree with you that I think one of the real issues is how are we, as a people on this planet, going to organise that decision-making ability? How do we cooperate? So sometimes I feel despair. In other words, people are so greedy and etc. that they're never going to cooperate. They're always going to be looking out for their own particular interests. And then on the other hand, I think, well, there are a lot of Chinese, to be very particular, who have a quite serious pollution problem around Beijing, and they are actually developing an electric car industry which is a lot cheaper than everybody else's and a lot more effective and efficient. And they have a large number of people in the world who will drive around in these machines within their own economy within the next 10 years. And it may be that the Chinese and then maybe the Indians, who both have pollution, severe pollution problems within their own countries, which are beginning to hurt their middle classes. And of course, there may be a small middle class in China, but once you get 100 million millionaire pluses in China, you suddenly realise the scale of their economy. And these people don't want their children suffering asthma, etc., etc. So there are serious problems with pollution, and if they solve the problem locally, it may end up that they provide a technology which just takes over from the oil-based technology of the West. So that's why I think your point about how are we going to get cooperation, how are we going to get decisions, who is actually going to take control of this process. I think that's one of the most important issues of the whole thing, almost more important than which particular technical solution. I mean, history shows that whatever solution we think of now, in 10 years' time, we'll probably laugh at it. So there's probably going to be smarter solutions down the road. So the more important thing is how are we going to organise ourselves. Sorry.
I mean, that's the reason why I ended up, focusing on it in the end was the fact that I did feel like this was the most pressing issue, not only in terms of beginning to think how we organize within countries and between the different countries, but also thinking in terms of just effective international frameworks, because looking at, for instance, NROD, which is the framework that is meant to prevent the misuse of weather modification schemes, it seems to be yet another formality that's not enforceable, that cannot hold anyone accountable for what they're actually doing, and it's only there in place to essentially tick this box of having something, that we could call upon should we need to. But the real question of how you end up going beyond national interest to work on an issue such as climate change, I think, comes into play here as well when it comes to weather modification.
I'll add my agreement to what's already been said, and in particular, Sofija, I liked your point about non-local effects and kind of unintended consequences. I can quite easily believe that we could engineer the globally average surface air temperature to be any value we want. I mean, we could pick 15.2 degrees and then we do some engineering to make that happen. But the climate system is more than just the globally average surface air temperature, it's the precipitation patterns as well. And I'm certain that changing the geoengineering the temperature would have knock-on consequences for rainfall that could be catastrophic. The climate is changing, temperatures are changing, precipitation patterns are changing, and to try and correct all of these problems using geoengineering seems to me to be on the fanciful side, I have to say. I was going to ask John for your opinion on an idea that's been going around in the atmospheric modelling community as a mathematician, your expert view on it, and you showed a beautiful picture of clouds and the fact that we'll never be able to have those in our models explicitly. But the idea is that because they're turbulent and random and chaotic, should we in our atmospheric models put some random numbers to try and capture the effects of those chaotic motions? This is called stochastic parameterization in the atmospheric modeling community, and I wonder what your view is on whether calling a random number generator in our computer codes is a good idea, because there has been some resistance to it, quite understandably, I think.
Yes, personally I don't like putting in random number generators, so to speak. So I've always preferred, so to speak, definitely doing something, even if it's the wrong thing, rather than doing a shotgun approach and just sort of crossing your fingers. But of course you can argue it both ways. So I guess the problem is, it's really been the issue that took weather people almost, well, more than 50 years to understand. And that is, you seem to be able to do a quite good job in predicting how horizontal pressure patterns and weather systems move, and a very bad job at predicting or understanding or simulating how things move in the vertical. So all the best weather forecasting programs, apps as you'd call them now, but they're just giant apps, because you have hundreds of millions of variables that have to be updated every few seconds. So these very, very complicated apps are trying to, in fact, produce horizontal weather in the way we understand, while assuming that vertically things adjust and balance out. And the question is, how do you do that? So one way is to, so to speak, pass every 2 or 3 time steps. You just sort of smooth out the computations and cross your fingers again and hope it keeps going. And we've been doing better and better at that, using quite a few different techniques. So then you get the really extreme other view, which is, but hang on, 20 years ago, people learned how to data mine in an amazing way. You can search for anything now on your computer, and there's no science behind searching for this information, inverted commas. Very good techniques for simulating and finding information. So why don't you just use those computer search techniques on the big data that's all around us and see what it predicts for climate? So you might argue that that's the practical person. The practical person says, well, forget about the science and the math and everything else. Just build a very effective program. So I'm sort of old school in the sense, well, in lots of senses actually, but I'm old school in that I feel that you should always respect the underlying science. So I don't know whether or not that's going to be proved true in the long run or not. But philosophically, you're in the position of, if you lived in that, so the movie of what, was it 2003 or so? Where you went into this simulated world on a different planet? Avatar? So what would be the difference between living in a real world versus living in a computer world? So what are you doing when you simulate the climate on planet Earth? So it leads you to the question, so you're sending information that's coming off your computer and you send it to the other side of the galaxy where there's intelligence. So the intelligence that's over there could be rational, but it might not be intelligence as we recognize it. So how would this intelligence take our signals? Would it say, oh yes, you're sending me music now. Oh, you're sending me chess games now. Oh, now you're sending me, oh, hang on, what are you sending me? Oh, is that what you call a real world? So what is the difference between a sort of an idealized mathematical scientific conception of a world and what's actually happening out there that we sort of experience? Which has been, you know, this question's been around for at least 2,500 years that we know about, written from the Greeks and presumably argued before even that around the campfires. So what's the difference between, so to speak, dream, which is what a computer is now getting you these days, a very, very sophisticated dream, but it's still a dream. It's a creation out of minds, human minds. And what's the relationship between what you're doing with that and what is actually happening around you? So it's a sort of interesting question that you might think about while your damn program won't work. and you're thinking about what on earth to do with the program. So my view is try and stick with the science if you can to underline the program. So what I ended up saying in the book was that one way you could, so to speak, fake this is if you did the scientific calculations to only, for instance, 10 or 20 decimal places, but you put the science in always to machine accuracy. So every time you do a computer calculation, as whatever your computer's accuracy is, 40 decimal places or what, you always put the science that you know and believe in at that level. And then you put all the things you don't know, which you then simulate. And of course, we're in a paradox, aren't we? Because the more and more accurately you try to represent the atmosphere on a computer, the less and less data you have to actually sort out the initial conditions for all the points on that computer. So what we do at the moment is we interpolate with other computer programs where we average and smooth and move that data. So we have satellites that observe 10% or even only 1% sometimes of all the data points around the planet. So you saw Paul's figures for the North and South Hemisphere. And you saw the really dramatic change that's happened in the last 20 years. So that's because of very clever computer programs that smooth out the unknown regions where we don't observe and we don't know. And you smooth it out and you fix that in the computer program and then you compute. So you might argue that in some sense we're already inventing numbers to put into the program. Why don't I just be a bit bolder and use a random number generator? So the answer is I'm sort of squeamish. I don't want to.
Right, so now before we open up the discussion to the audience as well, I would have just a question for all of you. So assuming that we are not living inside a dream, and we have to fix the problem that is climate change, so what is your personal opinion on how desperate should we be before actually trying some aggressive weather modification or any kind of really artificial control of the weather and the climate that goes beyond just trying to undo the damage that we've done. Considering we've seen in the talk how difficult it is to forecast the weather for several different reasons. We have to work with chaotic systems. And we've also seen that humanity doesn't really have a very clean record of controlling the weather in the past, and this has been actually weaponized as well. So, do you think should we never ever resort to this kind of thing, or is there a limit where we can say, okay, the science is advanced enough that we can say yes, this is a safe measure to take?
So it is probably useful to think about the military analogy here. Because in some sense, during the Cold War era, we did see both the US and the USSR acting out of a sense of urgency when the science was not ready. So even after the act of, for instance, cloud seeding in the Vietnam War, no one can tell you at this stage if this was successful or not. So they did it for 5 years. They want to extend the monsoon season, and nowadays, I believe most researchers in the field think that this is actually not effective, or you cannot say with a high degree of accuracy that this is effective or not. So along the lines of what we've seen with the wedding company, it's a shot in the dark and it might work sometimes, but there is no actual science which tells you this works. We know that this works. And as long as this is true, I think that acting out of a sense of urgency does not justify, we cannot be desperate enough and act on a sense of urgency when the science is not ready. So as long as prediction is not good enough and you cannot say with certainty whether or not your techniques are going to work, there is no level of desperation that we can be at and still justify action if the science is not ready.
Yeah, yes, I would agree with that. I mean, I just have a very bad feeling about this whole notion of deliberately modifying the weather. It can't be a good idea, can it? Just because we really don't, we know so little about how the atmosphere might respond to all of these experiments. And this is the only planet we've got. We're not going anywhere else if it goes wrong. And as I say, small changes in precipitation patterns will have a catastrophic effect because of our dependence, our societal dependence on water availability. So I'd like to suggest that we should never get to the stage where we need to invoke all of this. And there is a saying, actually, that I've heard people say that we should do research into geoengineering. So there's two schools of thought. Should we be funding research into deliberate weather modification or not? And the argument that we should be actually comes from people who are opposed to it. And the argument is that we need to do the research just to show what a bad idea it really is, actually. And I think I tend to fall into that school of thought. And when we could stop climate change, we could cut our CO2 emissions today if the political will was there. We're not stupid, we have the solutions, we know about renewable energy, we know how to build a nuclear power station, we know how to decarbonise the economy. There's just the political will doesn't seem to exist at the moment. But if climate change gets particularly bad, maybe political will change and there'll be more support for decarbonisation. But I think if we're starting to get to the point where we're relying on weather modification, things have gone really, really bad. I mean, they're already really bad, but things have got even worse, very dramatically. I hope we never reach that point, because our knowledge of what the atmosphere might do is at the moment very limited, and there could be really catastrophic, unforeseen consequences.
Well, yes, I suppose. So one way, for instance, that we might get it all wrong is it might turn out that the best way to modify the weather is to start getting snow falling on our highest mountain ranges again. So if you look at pictures 50 years ago and compare them with pictures now, what's quite dramatic is to look at, for instance, at the French Alps and look at the amount of snow throughout the winter and how deep it was and how much it covered of the ground, and then look then and compare that with now. So it might turn out that the best ways to change climate in the future, perhaps 10 or 20 years down the track, are actually just getting moisture out of the air and putting it on mountain ranges. That might turn out to be the most effective and safest way that we can actually modify the climate.
Could we just paint the mountains white?
That's a different sort of, that's to reflect the sun. You're quite right. So the point Paul's making is that very small changes in the amount of solar energy coming in versus and the amount going out will actually make quite a big change to the climate. So things that I would like to see happening, for instance, are lots more solar energy being used to desalinate seawater, for instance. So why don't we have thousands of acres of solar farms on the west coast of Africa desalinating the water and just pumping fresh water back into the Sahara to recharge the aquifers? You know, there are societies that were living there 500 years ago that were living on the underground water. Very rich cultural societies. So why aren't we doing things like that? There are a whole lot of practical things we want to do, things that politicians, so I think the last people I think are going to help us are the politicians. I think it's actually going to be commercial realities. It'll be the money that drives the decision making in 10 or 20 years' time. So that's my own personal view.
All right, thank you very much. So now I would like to ask if there's any questions from the audience that you would like to address to the speakers. Yes.
So thank you very much for the talk, by the way, it was very good. I think earlier John mentioned China in terms of their efforts in tackling the emissions. So just to make a point first and then ask a question. But the Chinese efforts in sort of electrification of the cities and electrification of the transport has been largely due to the Xi Jinping thought, which is the new sort of I don't want to say commands from Xi Jinping, but his equivalent of Mao Zedong's like Red Book. And when he puts this down, when he talks about it, he puts it within a framework of not necessarily only to combat climate change, but in the framework of it is for China's political and economic development. So there are issues. There's issue. It's somewhat problematic that he's putting, these efforts to battle climate change as essentially like a means to an end of economic and political development and power. So in that kind of vein, what do you think is as academics, what do you think we can do to stop the misuse of climate modification, etc.? How can we impact the policymakers, given that they don't really listen, or given that they're generally shit? Yeah. So how do you think we as academics can make a difference?
Who would like to take that question?
Do you want to say something, or you? No?
These academics.
Right. I suppose what I was trying to get at is that I think it's a good thing if we have perhaps 3 or 4 major economies who can actually do something serious at the planetary level. We've been locked in a system whereby we've been thinking there's only 2 systems. And if we can get into a system where there's 3 or 4, it might become so complicated. Well, when you're playing cards, when there's 3 people playing cards, it's a really quite vicious game, isn't it? Because you don't know randomly when one person will turn around and support the other. So a 3-handed card game is a very hard card game to play. So it may be that as we get more powerful, for instance, if the German economy leading Europe, the Japanese economy with the non-Chinese part of the Southeast Asia, and the Indian economies, if they all become super powerful to rival American economy, we might actually start seeing cooperation forced on us as a planet. And that's maybe that's going to be hopeful for us all, because, it'll just be pragmatic, that you actually have to have some rules. Because anything else will just be too terrible. And those economies will be able to make more money and thrive, providing they have rules. But it will mean that we'll have to live by those rules. But you're quite right, there's a downside, because China's also opening a coal power station every week. Yes, I'm just assuming you know that. So I'm not taking a simplistic view that producing electric cars in Beijing to sort out the pollution there is actually going to solve all the problems. There's a secondary issue, which is then cleaning up the coal-based power stations, for instance, and trying to get electricity without actually having to depend on oil and coal.
All right. Other questions? Yes.
Hi. So on that point, you're talking about nations banding together to try and reduce the effects of climate change. Unfortunately, the leading research is in the Northern Hemisphere, and judging from climate change predictions, a lot of those countries affected are going to be in the Southern Hemisphere, such as Bangladesh particularly. We do have stuff like the Paris Agreement, but how can we incentivize these nations even further to kind of get involved in research and actually implement it in their regular infrastructure, when really they're not the ones that are being affected in the short term?
Right, yeah, I see where you're coming from, and you're quite right. The major, what we call Western and what we're going to refer to as I saw one book that said the monsoon economies, and it pointed out that already nearly half the world's population is living under the Southeast Asian monsoon, defined in its broadest extent, which includes India and Pakistan. So if you draw a big balloon round, almost half the world's population is in that balloon, and very soon half the world's economy will also be in that balloon. So that's a rather big change that's happening to us at the moment. We'll probably be finished in about another 10 years' time, in that the majority of the world's economy will then be in that sector rather than in the Western sector. However, if you go back to Bangladesh, which is often said to me, I actually think to myself, there was less than 1 million people organised themselves in Holland with a few spades and a couple of donkeys and a few ox. And they actually built dikes. And they live in a place where a lot of the country is actually below sea level already. So we shouldn't panic. If actually there's a 50 million people that could actually get together with spades, and we actually have a lot better to help them in Bangladesh, and they could build a set of levees and canals and whatever, and actually transform that economy and that country. So we shouldn't panic about particular places. I think it's more of a general issue that we need to worry about. But of course there is the issue of there are always going to be hard cases, and it'll be interesting to see whether the world gets a little bit more compassionate and the United Nations gets a bit more useful. I mean, actually defining genuine little areas where they can help and being of real help would actually be a good start.
Right, thanks. I think we are slowly running out of time, so I think we have time for one more question. Yes, please.
So following on from the Bangladesh example, and the question, should we control weather? Suppose there's lots of rainfall in Bangladesh. Should we be able to control that rainfall in a certain area to say, let's say, 2 million people?
So
For short term, there won't be a major long-term effect. This might be only for 2 days. But
So if you want to have some nightmares for today, because today is the sort of pink chocolate day of the year, some sort of nightmares are that you very slightly change the humidity in the world and the warmth, and the viruses love it. And so the viruses destroy the rice crops, and we have no more rice. So now you have a serious issue. And I think that's the way that climate change is going to impact in the next 20 years. It really isn't going to be 1 or 2 Pacific islands having to be built on a few more stilts. That is not going to be the issue. And I'm sounding a little bit harsh about people from Bangladesh, but I really do think that if there was some goodwill and a bit of sensible engineering planning, we could actually protect Bangladesh in the same way that the whole of the Netherlands was protected over 100 years ago.
Maybe just adding on to that, I think some of the data do show us that the Netherlands, for instance, is amongst like the top European polluters, even though they would be still are most likely to be affected by climate change. So isn't this still an issue? The fact that even the countries which are potentially going to be affected more than others in their environment are still contributing more than those in their environment.
Right.
So how do you still, where's the incentive for the wealthy, the developed world to start moving at a faster pace?
Probably depends on how idealistic or optimistic you are about other people's behaviour. I mean, I suspect that that if you look at the present American government, you might think they are not really going to put $1 trillion behind helping the poorer people in the world. It just won't happen. So we might actually need other sorts of solutions. We might need to actually cooperate and make changes in other ways. We might have to stop thinking about, that's the way it's going to happen. I mean, what is going to affect them? So if you're a sort of sneaky person and you look at the maps, you might actually be more concerned about the flooding in Florida. Not because I have any sympathy for the people in Florida at all, but just because that actually will change Washington's behaviour. When the American middle classes who want to go down and retire in Florida, when they suddenly see their trillions of dollars of real estate going underwater, and by the way, they really will go underwater if you look at a map. So when that happens, then then people in America will get up and kick, as they say. Well, I won't be using.
So we see it's all about the incentives, and let's hope that we don't need too many incentives to start cooperating and solving these issues on a global scale. So I would say we are at the conclusion of today's discussion. So for those of you who are going to have dinner here at Lincoln, formal dinner starts at 7:15, so roughly 10 minutes. So you have time to go over there, put on your gowns, and enjoy. And for everyone here, including the speakers, thank you very much for coming, and let's give a warm round of applause for speakers.